This is a short video to review how to store single precision floating point numbers. So this is the layout of a single precision floating point number in memory. Now, the layout follows the general way we do scientific notation, but we're going to do it in binary. So just a quick review. When we do scientific notation, if we want to express the number 1.3 in scientific notation, this would be 1.3 e and then 0 or plus 0, because this is exactly where we want. Now, if we want to express the number 1300, right, this equals 1.3 e plus 3. So that is equivalent to 1.3 times 10 to the third. Now, we usually don't do this calculation of 1.3 times 10 to the third. We simply shift the decimal point over to the right 3 places, right? That will get us 1300. Equivalently, if we do 0.013, that equals 1.3 e minus 2, right? Which shifts the decimal point. It's going to take this 1.3 and shift the decimal point to the left 2 spaces, which is equal to 1.3 times 10 to the minus 2. Okay, that's just a quick review of your high school science class where you covered scientific notation. Now, we're going to do a very similar thing, except we're going to do it in binary. So it's going to look a little weird, but there's some things that are going to look very familiar to you. So the basic format is the same. We're going to take a number, a binary number, right? So we'll have a binary number n, and we're going to multiply it by 2 to some exponent. Now, the thing that's interesting here is if you write 2 in binary, right? That's going to be 2 to the 1.0, right? This is binary. So it's kind of cool because it has that like hook into scientific notation. So let's start with the number 7. Okay, that equals 111. Now, if we want to do this in the binary equivalent of scientific notation, we need to put the dot after that first 1, right? And if we want to multiply this by 2, so this is the binary equivalent of 2, we are going to take it times 2 to the second power. Of course, if we write that in binary, that's going to be 10. Okay? Now, so this is strictly the way you should write it. Now, because of the way we do the calculation of the exponent, we're going to keep the exponents as decimal numbers. So we're going to put that as 2. Okay? So that effectively shifts the decimal point over 2, which is going to result in this 7. If we look at the number 0.75, that in binary decimal or binary floating point is this number here, right? If you remember, the binary place values to the right of the decimal, they are 1 over 2 to the power of that place, right? So the first place to the right of the decimal is 1 over 2 to the 1 first power, which is 0.5. The next one is 1 over 4, which is 0.25. So the right side of the decimal of the point in binary is kind of difficult because the numbers get very big very fast. We're multiplying those numbers by 5, which grow much quicker than the numbers to the left of the decimal, which grow by 2 at a time. So that's why the right side gets kind of scary really fast. So we won't use big numbers here. But we want the number 0.75. Now, if we put that in binary scientific notation, that's going to be 1, 1, because we want the leading 1 to go here. And then we multiply that by 2 to the -1, because we want to shift this decimal point over 1 to get the 0.11. Okay? So with that in mind, let's take a look at these, how we would encode these numbers. So let's start. We're going to start with the 7. Let's see how we encode this 7. Okay. Now it's a positive number, so we're going to put 0 in the sign place. If it were negative, we would put 1. And then we need to encode the numbers here, this 1.11. Now the thing that is interesting about the way we encode these floating point numbers is we can do a little optimization that will give us a bit. It will allow us to have one more bit of precision than we otherwise would. The leading 1 is implicit. So in binary, the digits can only be 0 and 1. And when we write it in scientific notation, we get rid of all the leading zeros, and then we have one non-zero number, and then dot, and then the rest of the number, right? Now, since binary numbers, there's only one non-zero digit, which is 1, we actually don't need to record that. Like, we don't need to keep track of that because there's only one value it could be, unless it's 0. If the number is 0, then it could be 0. But we'll talk about that one special case in just a second. So the 1 is implicit. So when we write this number, it's just going to be this right here. Okay, and all the rest zeros. Okay, that's going to get us this part of the number. Now we need to look at the exponent. The exponent is kind of strange the way we do it. It's an 8-bit exponent, so you would kind of think that we would do 2's complement there, but we don't. We actually do the number. This is going to be I call it the exponent input. We generally refer to this as the exponent, but it's really the exponent. To get the exponent, we're going to take this number and we're going to subtract 127 from it. That's how we get the ability to do both positive and negative numbers, is by subtracting 127, which makes things a little odd when we just look at the number straight. So in order to get a 2, we need this number to be 129, so that 129 minus 127 is 2. So to get 129, we put a number 1 here, which is the 128 position, and then this will be all 0. Then we add 1 here for the 1, so 128 plus 1 is 129. And this is going to give us our number, right? This is going to give us 7. So when we look at this, from these digits here, we're going to get 1.11. And then we're going to multiply that by 2, the number 2, to the 128, or 129, 129 minus 127. Okay, and that equals 2. Okay? So hopefully everybody sees now how we got 7. So to do 0.75, we're doing 0.75 here. we first need to encode this part. Okay, now the one again is the one dot is implicit, so we only need to worry about the one bit here, and the rest are all zeros, right? And now we need to get this -1, right? So we need this part here to be 126, so that 126 minus 127 is -1. So 126, if we do this, and then if we set all these bits, it'll be 127. So if we don't set the last bit, it will be 126, right? And then of course we're positive, so we put a 0 here. So this is 127, right? The bits here form 1.1 times 10. Again, this is 2 in decimal. So 2 to the, and then we have 126 minus 127, which is -1. All right. So let's just practice going the other way, just to make sure this is all sunk in. Let's say we have the number where this bit is set here, and then let's say we have this here. Let's just change this to this right here, and then we'll make this be 1, 0, 1. Okay, and then all the rest zeros. Okay, oh, actually, just for fun, let's set this one to 1. And then all the rest zeros. Okay, so let's take a look at this number now. So if we look at the base, the n part, we can look at 1.1010001. Okay, this is what we're starting with. Now let's calculate the exponent here. Now, oh, we also have the sign, so let's take care of the easy part here. So it's negative. And if we look at this number here, this is 128 plus 3. So this is 131 minus 127, and that's going to be 4. Okay, so what this means is we need to shift this decimal point by 4, right? We're going to shift all these bits over by 4. So this is going to go 1, 2, 3, and it's going to end up right here. Okay, so let's write this number down here. So this is going to be 001, and then we have 0, 1, 0, 1, 1. Okay, so when we calculate this number, this is 2 plus 8 is 10, so it's 26, right? Plus 0.125, which is 26.125. All right, does that make sense a little bit? Let's do one more number. Oops, before we move on to that other number, we did forget about the sign bit here. So this number is actually negative 26.125. Okay, so the sign bit's kind of the easiest part, so it's easy to forget, but it kind of makes us completely wrong if we forget about it. Okay, so let's try a different number here. This time, let's do a positive number, so we don't have to worry about forgetting the sign. Okay, so this is a reasonably simple number. If we calculate what the starting point is, we get 1.1. Again, this is in binary, right? 1.1, the 1 is implicit. And then we calculate this number here. Well, okay, this is kind of a big number. If it's all set, it would be 127. However, this bit isn't set here, which is the 2-bit, so it should be 125. So we have 125 minus 127, right? And that's going to be -2. So that's our exponent, is -2. So what that means is we're going to shift this dot 2 places to the left. Okay? So we shift it once and then again right here. So we need to put this 0 in. So if we kind of fill out this table down here, we're talking about the number 0, 1, 1. Okay? So in binary, or in decimal, that would be 0.25 plus 0.125, which is equal to 0.375. Okay? And it's positive, so we don't need to worry about adding a sign here. So hopefully this is clear. I highly encourage you to practice these numbers. One thing you should note is if you're trying to encode a decimal number and after the decimal point the number does not end in 5, you're not going to be able to encode it perfectly. And you're just not going to get the exact number, because anything you're going to come up with is going to be an approximation to that number. So floating point isn't always completely exact. The other thing that you might be asking yourself is, how do we encode a 0? Because we have this implicit 1, and for the case of 0, this needs to be 0. The way we encode a 0 is we just get super, super close to a 0. So we want the smallest number we can get, which is setting the exponent part to all zeros, right? That's going to result in 0 minus 127. So it's going to get kind of the smallest input we can possibly get, and then we'll set the rest of these to all zeros. So it's not exactly 0, but it's the smallest number that we can represent, and we count that as a 0. You'll also note that we can have a positive 0, and if we change this sign here to 1, then it will be a -0. So we can have a positive 0 and a -0. One other thing to note, we can also express not a number in floating point, and this is kind of cool. But if you have a mathematical expression that results in a number that's not a number, we can actually express that in floating point. If these bits are all set to 1 in the exponent, we count that as not a number. Okay? So there you go. Practice encoding some numbers, and I'll see you next time.